Okay, so the learning goals for this lesson is identify the possible cases for intersections of 2 and 3 planes, use equations of planes to identify information about the intersection of planes, communicate concepts to others using appropriate vocabulary, identify consistent and inconsistent systems. Now we're going to talk about intersection of two planes in 3D. There are different possibilities. First, two planes are parallel. Second, planes are coincident. Third, planes intersect along a line. So case 1 is when the planes are parallel. So let's look at the equation 1. So equation 1 of plane 1 would be x plus 2y plus z plus 8 equals to 0. Equation of the second plane is 3x plus 6y plus 3z plus 31 equals to 0. So let's look at a diagram of the situation. So plane 1 would be something like this, and this would be plane 2, right? So that's just, we can see how they're parallel. So in order to solve this and see where they intersect, right, we would look at the normals of each plane. So normals for plane 1 would be the coefficients of each. So 1, 2, 1. And then the normal 2 would be 3, 6, 3. So from this, we can see that normal 2 is just a multiple of 3. So we know that n1 is equal to 1/3 of n2, right? So since these are multiples, right, we can determine that the planes are either parallel or coincident. So let's just do this by solving in this case. So we know that 3 times equation 1 would give us 3x plus 6y plus 3z plus 24 equals to 0. And this equation 2 would give us 3x plus 6y plus 3z plus 31 equals to 0. So if we subtract equation 1 and 2, we get, this eliminates, this eliminates, this eliminates, we get -7 equals to 0, which is not possible. So planes are parallel. Now we're looking at case 2, which is when the planes are coincident. So the equation of plane 1 is 3x plus y plus 2z plus 8 equals to 0. And the equation of plane 2 is 6x plus 2y plus 4z plus 16 equals to 0. So a diagram of the situation. So if this is plane 1 or plane 2, plane 1 would be basically within the same plane. So plane 1 and that's plane 2. So now the solution. So first we find the normals of each plane, and as I mentioned before, we just take the coefficients of each x, y, and z respectively. So 3, 1, and then 2, and normal 2 would be 6, 2, 4. So now we can see that the normals are multiples of each other, right? So now we know that the first normal, so n1, is half of n2. So since the planes are scalar multiples, we know once again planes are either coincident or parallel. So now let's just look at this and solve for each. So we know that 2 times equation 1 gives us 6x plus 2y plus 4z plus 16 equals to 0. And equation 2 gives us 6x plus 2y plus 4z plus 16 equals to 0. So if these were equal, the left hand side and the right hand side would be equal. So if we subtract these, we get 0, 0, 0, 0. So we get 0 equals to 0, which is true. Therefore, the planes are coincident. So another way, just for external reference, another way to check if these two planes are coincident is that we can simplify the second plane into the first plane by simply dividing it by 2. So 6 becomes 3, 2 becomes 1, 4 becomes 2, and then 16 becomes 8. So we know it's coincident. So now let's look at case 3. But this time, this is when the planes intersect along a line. So the equation of plane 1 is 2x minus y plus 3z minus 5 equals to 0. The equation of plane 2 is 3x plus 2y plus z plus 13 equals to 0. So let's make a diagram of the situation. So since the planes intersect along a line, let's assume this is one plane. And then the other plane would be something like this, and they would intersect. So we know like something like this would be the line of intersection. So in order to look at the solution of this, and find the line of intersection, the first thing we would look at is the normals. So the normals of the first one would be 2, -1, 3. The second normal would be 3, 2, 1. So in this case, we can see that neither are multiples of each other, so the planes are neither parallel nor coincident. So in the previous examples, we determined that they were scalar multiples of each other, so we can determine that they were either or, but now we know that they intersect along a line. So now let's go back. So we know 2 times equation 1 is going to give us 4x minus 2y plus 6z minus 10 equals to 0. And then equation 2 is going to give us 3x plus 2y plus z plus 13 equals to 0. If we add these two up, we get 7x plus 0y plus 7z plus 3 equals to 0. So this would be our equation 3. So from equation 3, we have to assign a parameter. So let's say z is equal to t. So knowing that, we can say z is equal to t, then let's solve for x. So if we isolate from here, we take -3, we take 3 to the other side, so it becomes -3. Take z to the other side, so it becomes -7z, but then we divide it all by 7. So we get x as -3 over 7 minus t. Or we can just write this again as -t minus 3 over 7. So now we just basically sub these values back into our second equation. So we know 3 times, we know x is this, so -t minus 3 over 7 plus 2y plus z plus 13 equals to 0. So this is the parameter equation of the line of intersection. Let's just write this in vector equation form. So in order to get our initial point, let's just take t to be equal to 0. So if t is 0, we know that x is -3 over 7. We know that this y would be -5 over 7, -5, 6 over 7, and we know that this z would be equal to 0, plus t, -1, so we just factor up from there.
Now, identifying the intersection of 3 planes in 3D space, there are many more ways in which 3 planes may intersect or not than 2 planes. Case 1, where all 3 normals are collinear. First, all 3 are parallel and distinct. Second, 2 planes are coincident, and the third is parallel. And third, all 3 planes are coincident. Determine any point of intersections of the plane. So plane 1 is 2x minus y plus 5z plus 4 equals 0. Plane 2 is 4x minus 2y plus 10z plus 15 equals 0, and plane 3 is negative 6x plus 3y minus 15z plus 7 equals 0. Here, the three normals are n1 equals 2, negative 1, and 5, n2 equals 4, negative 2, 10, and n3 equals negative 6, 3, and 15. So the diagram of the planes is they do not intersect, as like we don't see any point of intersect, but they are parallel. As we can see, they're like multiple, like the scalar multiple of like first plane. So now looking on to a solution, it's n2 is equal to twice the n1, but the equation for plane 2 is not the twice for plane 1, as the digits are different. Similarly, n3 is equals to negative 3n1, but the equation for plane 3 is not thrice of plane 1. Therefore, the planes are parallel and distinct and okay, so next case is where only two normals are collinear, two planes are coincident, and the third cuts the other, where intersects a line. Two planes are parallel and the third cuts the other, where it's inconsistent. Finally, the case 3, where none of the normals are collinear. Normals are coplanar, planes intersect in pairs, which is inconsistent. Normals are coplanar, planes intersect with each other, where intersection is a line. Normals are not coplanar, where intersection is just a point. Coplanar is when normal 1 dot normal 2 crosses normal 3 equals to 0, while non-coplanar is when it's not equal to 0.
So now with equation number 4, we basically just add them together to eliminate z. So we get 4x plus 4 equals to 0. Then we solve for x as negative 1. Then we sub that x value into equation 5 and we solve for z as 2. Then we sub x and y values accordingly into equation 1 and we solve for y, which is 3. So in this example, we're going to be focusing when the normals are not collinear or coplanar. So let's just look at the equation of the plane. So it's going to be x minus y plus z plus 2 equals to 0. And the second plane, x minus x, 2x minus y minus 2z plus 9 equals 0. And the third plane, 3x plus y minus z plus 2 equals 0. So then the normals of each are going to be the coefficients. So 1, negative 1, and then 1. 2, negative 1, negative 2. 3, negative 1, positive 1, and then negative 1. So from right off the bat, we can see that none of these are collinear, so none of them are multiples of each other. So the next step is going to be checking if they're coplanar. So to check if they're coplanar, the first normal is going to be the dot product of the first normal, and with the cross product of the second and third normal would be equal to 0. But when we work out the dot product, so the cross product comes out to be 3, negative 4, and 5, and the dot product of this is a non-zero vector. So since the triple scalar product is not 0, that means the normals aren't coplanar. So this means that we know that the three planes are going to intersect at a singular point. So now we're going to solve by elimination. So we have our first equation, our second equation. We subtract equation 1 by equation 2, and we get our third equation, which is negative x plus 3z minus 7 equals 0. Now we have to go and find another equation in terms of x and y only. So we get our second equation and third equation, like for the second plane and third plane, and we add them. So if we add them, we get 2x plus 3x, which is 5x, and then we get the y gets eliminated, and then we get negative 3y plus 11 equals to 0. So in this example, we know that the planes are coplanar and they're going to intersect along a line. So the equation for plane 1 is x minus 5y plus 2z minus 10 equals to 0. For plane 2, it's x plus 7y minus 2z plus 6 equals to 0. For plane 3, it's 8x plus 5y plus z minus 20 equals to 0. So the normals are 1, negative 5, 2, 1, 7, negative 2, 8, 5, and then 1. So we just do the triple scalar product of these three normals, and we get the answer to be equal to 0. So since the triple scalar product is 0, so we know that they either intersect in a line or they not at all. So now let's start with equation 1 and 2. So if we subtract equation 1 from 2, we get negative 12y plus 4z equals to 16. Now we get another equation by multiplying 8 of the second equation and 3, and we subtract them, so we get 51y minus 17z equals to negative 68. And now if we get this equation and multiply it by 4 and multiply this equation and we subtract them from each other, we get that every z value and y value are consistent. So like the equation is true for all values of y and z, so that means that they intersect in a line. So now we have to set parameters. So we set z as equal to t. So then we know that from equation 4, we know that negative 12y plus 4z, which means that we place t, equals to 16. Therefore, we get y as 1 over 3t minus 4 over 3. So we set z as t, and then we get y as 1 over 3t minus 4 over 3. Then we sub this value back into our second equation, and then over here, and then we solve for x. And we get x as 10 over 3 minus 1 over 3t. By setting t as 0, we can solve for a point that's on the line, so we get 10 over 3, and then over here we set t as again as 0, we get negative 4 over 3, and we set z as 0, we get thing. And we factor out t from each of them to get the vector equation. So the vector equation would be 10 over 3, then negative 4 over 3 and 0, plus t, negative 1 over 3, negative 4 over 3, and then 1. So this is our first application question, and we're going to check if the planes are perpendicular and then find the point of intersection. So plane 1, this is the equation, and then this is the normal, so 1, negative 1, and 1. This is the equation for plane 2, 1, 2, and then 1 would be the normal. And this is the equation for 3, so 4, 0, since there's no y, and then there's negative 4 for the z. So from this, we see that none of them are collinear, and then we have to check first to prove if they're perpendicular. So to prove if they're perpendicular, we check the dot product of the normals and check if they're perpendicular. So for the dot product of the first plane, the second plane, we got 0, so we know that sine 90 is 0, so we know that these are perpendicular. Similarly, the dot product of normal 2 and 3 are perpendicular, and dot product of normal 1 and 3 are perpendicular. Since the dot product is 0 for each planes, that means that there's going to be a point of intersection, since all of them are perpendicular to each other. So now we're going to basically sub in values into and then try solving. So let's start with our third equation and rearrange for x in terms of z. So we take 4z to the other side and then divide their side by 4, and then we get x is equal to 15 over 4 plus z. And we sub this into our second equation, which is this one. So what we do is we get x plus 2y plus z equals to negative 9. Then we sub this value in and we solve for y, and then we get y is equal to negative 51 over 8 minus z. So we sub this now into our equation 1, which we get x minus y plus z equals to 8. So we solve in our x value, which we solve for here, and we sub in our y, and we then we just solve for z. So we get z as negative 17 over 24. Now to solve for the rest of the thing, we sub z into our second equation here, and we can solve for y. So we get y as negative 17 over 3. Now to solve for x, we sub our z value once again into our x equation here, and then we solve for x.